Hello, everybody. Is it going?
It said that it's going live. It takes normally a minute or two for it to actually pop up on YouTube.
Okay,
So I
I'll
haven't
just
seen it
kind of
yet.
go then. And
There it is.
all right, sweet.
We are
Okay.
live.
Sweet. So, hello, everybody. This is gonna be a discussion with Michael Van de Graaff, otherwise known as Tapioca Weasel. Hopefully everything goes smoothly here. Not done this before, but we're gonna just go with it. And Michael, he's an awesome guy. We've been talking. Very nice. We got our hearts in the right place. Very similar, a lot of overlap. This guy is ridiculously smart, and he it's in his family tree very bright. And so we are going to be talking here specifically about molecules, density, gravity, the atmosphere. And so Michael, I will let you introduce yourself. Say what you gotta. Wonderful to have you on, man. Really.
Awesome. Thank you. Yeah, Nathan, it's great to be here. Yeah, I'm Michael Van de Graaff. I am a physicist working at Stanford University. I work in experimental ultra cold atomic physics. So we use lasers and magnetic fields and stuff to cool down molecules and atoms. Atoms, not molecules. Molecules are too hard for me. Other physicists do molecules, and we cool them down in a vacuum chamber using lasers and magnets, and slow them way down so that we can study their quantum mechanical properties and do stuff like that. And that is the reason that I am very interested in the particular questions of how gases behave if you release them inside like containers, and whether or not a gas can exist next to a vacuum without like a physical tangible barrier in between. I claim the answer is yes, and I do it at work every day. And that's what we're going to talk about. So I'm not here to argue against the flat Earth. I do not believe in the flat Earth. I want to be clear about that. I am unaware of any physicist who has received a PhD in physics from a legitimate accredited institution on the planet. I'm unaware of any person like that who believes that the Earth is flat, and I will not. But that is not why I am here. But I also do not want to give any um, misapprehensions about what it is that I believe. I also happen to be an atheist. I understand that Nathan is a Christian. I was a Christian for most of my life. That also is not what I am here to argue about. I have no desire to convince anybody to become an atheist or anything like that. I want to talk about, will a gas fill a container, and can you have a gas right next to a vacuum without a physical barrier?
Yes. Awesome. Excellent, Michael. And yeah, so this is not going to have anything to do with those other topics. We're just going to try to lay down some groundwork, clarify some things, and really try to help everybody get as much of an understanding as possible. So no matter what side you're on or what your views are, you can be more approachable and be able to give more accurate information, because information does a lot in this world, in this time that we live. Accurate information is so vital to so much and can have some pretty profound rippling effects. And so Michael is gonna be really the guy to really talk about a lot of this stuff, because he works with it. He's experimental physicist. I just want to emphasize that. That is neat. And so we got a bit to talk about here. And so I guess let's see. So the first thing about the we could jump right into the barrier. So containing gases, typically when we see a vacuum, we see that to create a vacuum here with machinery, there needs to be some sort of outside container, and then you suck molecules out from that. You extract them from within the container, and it creates a very, very low pressure area, low particle density, and you get what we call what is a vacuum. But there's a barrier there. So, Michael, would you like to talk about how you create gases suspended without a vacuum or without a
So I
barrier?
think I think it actually makes more sense to start with the related topic of will a gas expand to fill a barrier, because for for one, if I can give you an example where that doesn't happen, then I have already sort of answered the second question, right?
Yeah. Okay.
So so that's a good question. So the question, and I think where a lot of the confusion comes from is the way we are taught what a gas is. So how would you define a gas?
I would say a gas is a state of matter. It's got high energy. The molecules of the gas are not connected in any way, so they don't have any particular shape compared to one another. They don't form like a crystalline structure. They move past each other very easily, or collide off of one another in collisions. Uh, they're not necessarily like semi-bound like water. And they do occupy the available space, the shape of their container, that they're able to. I actually personally, I think they're kind of more of a fluid.
They are a
True.
fluid. They are
Yeah,
absolutely
but
a
they're
fluid. Fluid does not mean liquid.
no, yes, and that's
Yes, it means
fluid.
a thing that flows.
Yes, and that's what I think. Like people think of fluid and they think of liquid, but I think that a gas has more true expression of characteristics of fluid than a liquid does, because liquid has to be completely the volume of the container has to be full of liquid, whereas gas will try to occupy that whole area
Mhm.
without needing as much of itself. Um, and there's a lot of um, space between the molecules. I mean, a lot on an atomic scale. Whereas liquids tend to be very close and are rubbing up against each other and trying to kind of make their way around. Um, and then in liquids and everything too, you can get like
Yeah,
you can
so
dissolve things and there's
let me just
charges.
cut
And,
in there for a
yeah.
moment. So, another way of sort of describing several of the ideas that you've mentioned here, and you're absolutely right about filling the available volume, because that's slightly different than what you might intuitively expect. Um, but the one way of saying that is that gases are compressible. They, if you change, they don't have sort of a steady density over a wide. They obey roughly, and you already identified some of the ways in which this isn't true, but they roughly obey the ideal gas law.
Mhm.
So the ideal gas law, right, is PV equals I can't remember actually if it's little n or big N. It depends on if you have R here or K here, but it's either the density or the total number. And so we got pressure and volume. The product of those is going to be proportional to the temperature. So if you had just like a box of like a normal gas and everything, and if you doubled the temperature but did not double the volume, then you would double the pressure, right?
Mhm.
Whereas for a liquid, if you double the temperature but don't double the volume, the pressure inside the liquid doesn't really change.
Yeah, and
So,
it's with the compression, one thing for to kind of get a visual is if you have a syringe with a plunger on it, if
mhm,
you fill it with liquid
yeah,
and you put it to your thumb, you can kind of squeeze it down a little bit. But if you do it with gas, you can push it down really far, and then when you pull the plunger back up, you can actually feel the suction on your thumb because you are expanding the volume. You're not
mhm,
changing the temperature, so you're dropping the pressure, and your
yeah.
thumb would feel that.
Yeah, while you're doing it, the temperature would actually drop a little bit as you do it, but it would immediately get warmed up by the fact that it's in contact with
The room
the
temperature
syringe that you're
environment.
holding. Yeah, exactly. That's
He's
exactly right.
technical. He's good.
Yeah,
Mike, you're
yeah. I look,
good.
and this is a thing that I often nitpick when people on my side, I'll say, try and do things like debunking or whatnot, is they will say something which is like 99% true, but like technically in this one, like you have to, like, you got to be specific and precise.
Yes.
And I'm here to do that.
And it's completely fun. If you're gonna you help me get my language more precise, that is, I mean, it helps that because it's what I mean. The goal is
And
to be as precise as possible, so we're getting the best understanding. So I think you're right on with like the whole a lot of my premises for these types of things. So that's why I'm
yeah,
again really happy to have you on here. So I'll let you get back to it. So
yeah. So, but this is the ideal gas law, right?
mhm.
What the ideal gas law presumes is that the particles are point particles. Each atom doesn't have volume so they don't have volume, so they don't take up any space. So the volume is just like the volume of the box in this case. You don't have to subtract out the size of all of the individual particles. Now you can modify this by including a term here. I can't remember exact. I think it's called the Gay-Lussac law, but it's something like P times like V over like minus R cubed times N or something equals NKT. Because here, if all of your if all n of your particles are a cube in this case, I mean it's actually a sphere. You'd put a thing for a sphere here. 4/3 pi somewhere. Okay, well now that just looks like a Chinese character, but it's fine. Then you'd have to subtract all that out, because imagine if your box was like this and your particles are this big, right? Like eventually, if you get a lot of them, you're gonna run out of room because all of the particles are just gonna be jammed next to each other.
They're
So
gonna go into closest packing.
yeah, exactly. So that is one way in which this is an idealization. Another way in which it is an idealization, and also in some sense, almost, and this is one of these things that I'm going to say that would be easy to quote mine me. In some sense, this is almost self-contradictory because it's also assuming that the particles are not interacting. You mentioned correctly that the particles could collide with each other. The ideal gas law does not
It doesn't account for
include
energy
that.
loss, right?
They only hit the walls of the container. What was your question?
It's like it doesn't account for any energy lost in the exchange of a collision between
Yeah,
particles. It doesn't
yeah.
count
And
what they impart.
any inelastic change. So do you know what an elastic collision versus an inelastic collision is?
Can you define it?
Yeah.
Like,
So imagine you have two particles and they hit each other, and this one goes off that way and this one goes off that way. If the total kinetic energy, so this one has KE1 and KE2, these are the kinetic energies for that particle, 1, 2. So particle 2 has kinetic energy of KE2. Kinetic energy is 1/2 mass times velocity squared. Do you agree with all that so far?
hmm?
Yeah. So if those happen, and then this becomes particle 1, and we'll just call it prime. It's the same particle. And
Yeah.
then this one 2 prime. So if you have Ke 1 plus Ke 2 equals Ke 1 prime plus the kinetic energy of 2 prime, all of the energy associated with the motion of the particles, it still shows up in motion, then that is an elastic collision. Normal particles like billiard balls obey this to a very, very good approximation. Not perfectly. If they did, you couldn't hear them because some of that energy has to go into creating the sound wave. But most of it goes just into the thing, and so billiard balls are the canonical example that we use.
There's a small amount that is also dedicated to heat.
Yes.
Friction.
Yes.
Okay.
Yes. And all of the acoustic energy, for example, ultimately becomes heat as well, because heat is just kinetic energy, but at the microscopic scale.
Yeah, it increases the vibration of the molecule as it passes it, and increases its energy level.
Yes, in potentially a few different ways. If instead instead of billiard balls, for example, if instead we had little balls of clay, unfired clay, then what would instead happen is they would just hit each other and fuse.
Mhm.
And then all of that kinetic energy, suddenly at the end, it's not moving anymore. All of the kinetic energy has been converted into heat in that example. So that would be an inelastic collision. So elastic, the kinetic energy before and afterward is the same, and an inelastic, the kinetic energy is not the same before and afterward. You could also imagine.
So you could say, like, for elastic, you can think of like if you have rubber balls and they hit and bounce, like they're elastic, they're going to bounce, whereas inelastic is something that is rigid. So when there's a collision, it becomes rigid.
Well, it's something. It's actually more like something, because billiard balls. Do you think of billiard balls as being rigid?
Well, I'm talking like to conceptualize elastic versus inelastic. There's going to be motion after inelastic versus inelastic. It becomes kind of a sturdy point.
Well, it doesn't have to. Like, imagine. Well, the example I was going to go to was asteroids colliding. Sorry.
No problem.
But car crashes, for example. The cars are still moving afterward. Maybe, like, if you have two cars that crash, like, a lot of the energy has been lost in mangling all the metal. But also the cars are still moving. So it can change. So if, for example, you had a particle that, instead of being one particle, suppose particle 2 was a particle connected to another particle. It was a little spring, and you can't see that. You can't see inside of it. You can only see particle 2 just looks like this, okay? But all you see is particle 2. And if you hit that really hard, what you're going to get is this going to be going like this. And it's also going to be moving, but if you can't see that, you're not going to see that motion. So it might look like suddenly some of this energy, Ke1 plus Ke2, suddenly was greater than that, because maybe the first ball completely stops and the second ball goes off and is shaking, and some of that energy from before the collision is now hidden inside particle 2, and it's not visible to your detector as kinetic energy, even though particle 2 is actually two particles. And
it's just
those are both vibrating,
so it's not able to be expressed.
Exactly, but you can't see that. Now, that that could like if you just have an oxygen molecule could do that because they are connected by a chemical bond, and that chemical bond can act like a spring. But a solitary atom, instead of looking like that, it would look like that. A bunch of particles in the center, the nucleus, and then your electron over there, and there's
That
a
outer shell would be like the electron cloud.
Yeah, exactly. Exactly. So that is true. You'll only obey this law if all of the collisions are like perfectly elastic, or they're not colliding at all. But if they're not colliding at all, then you also can't get then the individual energy of any individual atom isn't going to change. It's just always going to have the same speed because it just bounces off the wall and it just comes off at exactly the same speed. So
and that's why it's called
they aren't
ideal
even in
gas
thermal
law.
equilibrium with each other. So actually, temperature isn't even well defined in a non-interacting system.
So that's why it's called ideal gas law, is because it's in a situation that isn't typical in an experimental collision of gases. You're going to actually get these losses of energy here and there, whereas ideal assumes keeping all energy conserved basically with each collision.
The other thing that the ideal assumes is, suppose you had a box and you had 10 atoms in your box, and they were not stuck to each other, so they were neither a liquid nor a solid. If they're rigidly stuck to each other, then they would be a solid. And they're not just one big molecule, because one big molecule, saying if that's a liquid or a solid is kind of missing the point. But these are independent molecules, and if they're all stuck in a lattice, like a hexagonal lattice of an ice crystal, then it would be a solid. But if they're all sort of just mushing around, but still bound to each other by, for example, surface tension, which is ultimately, I believe, caused by like the Van der Waals force or something. I don't know.
Yeah, London dispersion forces.
Yeah.
Van der Waals. And that's where you get kind of like molecules that do this sort of a thing, where they're not, they're loosely associated with each other.
My headset like glitched out for a moment there.
You're good. I can hear you now. You're good. So
fantastic. Okay. So yes, you're exactly right. London dispersion force. See, this is why I wanted to talk to you, because yes, you actually seem to be curious and interested in like actual science.
Definitely.
So imagine you had a box now with just 10 atoms in it, all moving around. Okay. But 9 of those atoms are very, very, very cold. They're very low energy. They're not moving very fast. And we're going to imagine, do I want to? Well, no, I'll get to that in a moment. But so if that's true, we got all of those atoms, and so we got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we've got number 10, and number 10 is just moving. It's just zipping all around that container like crazy. But it's an ideal gas, so it does not hit any of these. It only hits the wall. If it hits one of these, it just goes right through it. So would you expect, if you released this one in it for a little bit, what would you expect the energy of these particles to be after a moment in that situation where this one is really, really, really fast moving, and all of these start out totally stationary, and none of the particles can interact with each other?
Then their energy level would not change.
Yes. So they would not come into equilibrium, right?
Mhm. Yeah.
So that's wonderful. That's fantastic. Yes,
Because
because
just
you need to be able to in order for them to come into thermal equilibrium. Thermal temperature refers to the average kinetic energy of the particles in a system.
so if they were able to interact and try to go towards equilibrium, that high energy molecule would be interacting with the low energy molecules, and they would be the high energy would essentially be giving its energy to bring all the molecules into equilibrium.
Yes, exactly. Exactly. Perfect. So, because of that, you can only have thermal equilibrium in a system where you can distribute those energies, where the things can interact a little bit, just a little bit, enough so that over time they all hit each other. It turns out that if all of these molecules are the same mass, they're all the same mass, it turns out that it takes approximately 2.4 collision, that's a 4, not a 9, 2.4 collisions before the energy of that, the initial energy of that particle has sort of become washed out, and it's now just kind of on average the energy of all of them. It takes 2.4. Now you may be wondering, how do we know that number?
Yeah, and I'm
My
trying to think
advisor
like,
in
is that a
grad school
lot of
actually
collisions
published
or
a
not?
paper on this where he heated up a gas of atoms in one direction but not in the other direction, and then figured out how long it took before they started moving in the other direction as well. And they know you can calculate how often the particles collide with each other, and then you do the math, and it turns out that by the time you can no longer tell which direction you shook the gas originally, it takes about 2.4, maybe 2, maybe 3 collisions before it's all been mixed around.
That
So
that is something. That's a thinker, because like if you have two pool balls and they're heading towards each other and hit, they're gonna, off of one collision, they're gonna alter each other.
they're going to alter each other, but if you have one pool ball blitzing like crazy around a table, it's going to take a couple collisions because it's going to lose a lot of energy in the first collision, because like ballpark half of it or something it's going to go to one of the other ones, and it's going to lose less energy in the second collision, and then even less in the third collision, and eventually it'll stop losing energy because the other billiard balls have enough energy that when they collide, it might lose some, it might gain some, and it'll just keep on doing that forever.
That's 2.4. So that first one, if it hits 2.4 times onto another molecule, now that molecule and those two molecules are going to be going the same, velocity.
Very roughly,
Roughly.
it's more of what I'm trying to tell you. What I want you to get out of this is, how many times does this thing have to hit one of the other molecules before it starts to look like all of the other molecules? And that number is around 3.
Okay.
Around 3. It's not around 1,000, and it's not around, and it's not 1, but it's a
Okay.
lot closer to 1 than it is to 1,000.
Yes. But it's all
And
this all
also
has to do with energy trying to find equilibrium
yeah, and
within the
technically,
system.
this is even more precisely if you didn't have that, but you had. I'm gonna do it with just 4 instead. If instead you had it like this, so all of these molecules are going, but they're mostly going just straight up and down. They're not really going side to side, but they are a little bit, because 1, I'm a bad artist, and 2, I intended to be a bad artist. So they're going they're going a little bit, and eventually like this one's going to go like up like that and up like that, and up like that, and this one's going to hit, and then they're going to hit, and then they're going to ricochet. And what it really is that after all of those have gone about 2.4, then the direction of all of them has been randomized. That's it's sort of initially all of the temperature was all in this axis because they're all going up and down, but after they've bounced around a little while, now they're going in all directions.
And just a little while, because it only takes about 2.4 collisions, and suddenly the whole system is shaken up.
Yep.
And
unless it takes, if it takes 8 years to do 3 collisions, it's going to take a while. But if it takes 8 picoseconds to do 3 collisions, then it's going to be, for most purposes, almost instant. There are some
I'd give that a double arrow on a reaction, on a chemical reaction. That gets 2 arrows going forward. Like that's a very fast reaction.
Yeah, exactly.
So now, okay, so if you have these molecules and they are bouncing around, hitting each other, colliding, say you have this, quite a big container. Well, yeah, it would be a massive container. Say you have a really big container, and there's a certain excitation of these molecules. They have so much energy. Are they going to be able to cover the full cover the whole area of the box? Like, will the molecules be able to get all the way up and bounce off of the top wall? Or will they spend their time kind of knocking around, and if a molecule goes up, but the ceiling is too far away, would it just arc back down? Do we not?
You read my mind. You read my mind, Nathan. That was exactly where I was going with this. This is, yes, wonderful. Imagine we only have one atom in the gas, right? And that atom is here. And if that atom is going up, but it's not going up very fast, imagine, like, if it was a baseball, it would go like this. It would go, right?
Mm-hmm.
And it would just keep bouncing around.
It looked like solitaire, like when you win a game of solitaire on the computer, the card deck sprays out everywhere.
Yeah. So it would bounce around. So that would happen if you just had one atom, right? One atom. That atom would always stay in the bottom half of the box. That is presuming that when it goes up, it slows down, and then it comes back down and it bounces off the bottom. Now, I claim, generally speaking, if it's a neutral atom and you're not hitting it with something, it's just a particle with some mass moving around in a box. I would claim that the reason it stops going up and starts going down is because of gravity. We don't have to necessarily call it gravity, but things do go down.
Yes.
Like, generally, if all you have is just a thing, and you don't have any electric forces or anything else, because my name is Van de Graaff. Okay, I know what you can do with electrostatic forces.
Yeah. Okay. We'll just say, things do. No matter, I don't think I know anyone who doesn't think things go down. So that things do go down eventually. Would that molecule find a resting energy where it would just kind of, once it lost all of its energy, it would just kind of sit on the ground? Well, theoretically, this is theoretical.
That depends. How would it lose energy? Can it lose energy, for one? How would it lose energy? How would it gain energy?
Because this is like, like say you had a system where like outside temperatures couldn't get in to keep the molecules at a certain heat. And I don't know if this would be like absolute zero where it would where the ins within this container it would be going towards absolute zero. But if you had, like, I've wondered about if you had a box full of molecules of gas and they were moving around and bouncing all over the walls and everything, if you let that box sit there for a period of time, would eventually all of the molecules, they would hit off of each other, off the walls, lose a little bit of energy on each collision, and then eventually over time would those molecules settle down to where now all your gases are kind of um, spread out on the bottom of the container?
The very, very long-term answer to your question is yes. The short-term answer to your question is, as typical, it depends.
And just real quick, so if you have molecules, molecules that are not moving is considered absolute zero, right? If they're completely.
If they're yes. Now, because of a variety of quantum mechanical reasons, you can't get exactly to absolute zero, but you can get very, very close.
Yeah.
So we in our lab, we cool down the atoms so cold that they are only moving, an individual atom is only moving at maybe a few centimeters per second. Yeah, they're very close to absolute zero. The temperature, the last time I measured the temperature of the atoms in one of the later stages of cooling in our vacuum chamber, the temperature of those atoms was between 2 and 3 microkelvin. So it was about 100 million times colder than room temperature. Room temperature is about 300 Kelvin. And when we measure our temperature of our atoms, they are at just 2 to 3 microkelvin. That's very close to absolute zero.
Yeah,
But
that's.
it's not quite there.
Ooh.
The coldest I've ever personally measured a system, and I'll probably get on our experiment, we have ways that we should be able to get maybe an order of magnitude or so colder, has been 12 nanokelvin, so almost another factor of 1,000 colder than that, but that requires some other.
You're getting into a lot of decimal places. That's a lot
Yeah,
of sig figs there.
yeah,
That's cold, man. I was gonna
it's
make
very
a cool
cold.
joke, that kind of a small cool joke about your chilling atoms, but
Yeah, I
but
mean,
that's.
yeah.
Wow, man. That is really, really cool. That's you're like slowing an atom down to something that is like this small little unit of matter. You're slowing it down, something that's normally so fast to just a crawl
Well,
basically, and at temperatures that are mind-boggling.
yeah, and but you asked the original question you asked was, if we have a box like this, will they eventually go to that temperature? Now the long term answer, as I said, is yes. The reason for that, this is kind of missing the point of your question, but I want to be technical. The reason for that is also you would have black body radiation. You would have energy just radiating away from the system slowly. So the amount of energy in the box would slowly decrease and decrease and decrease over time, because it would just be released as black body radiation. But that would take a long time and whatnot.
Yeah, long
If you
time.
did this experiment, just if you just have a box of atoms just in a room, as we do, I mean, you like put a cap on your water bottle, boom, you've got a system. The thing is that when the atoms hit the wall also is made out of atoms that are jiggling really, 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 really fast, because they are at the same temperature as the rest of the room.
Mhm.
And temperature is kinetic energy of those little molecules. So what's actually happening is that box, the edges of it are vibrating, and when the atom hits it, if it's cold, if it's really, really, really cold, it's only moving at like a centimeter per second, it goes woo, boom, 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 because it's kind of like in a pinball machine when the ball hits the bumper. The
It's
bumper
getting a
has
jump
all this
start,
energy,
basically.
and it's just always blasting.
Yeah, like even though that molecule, as it's going in its arc, it's slowing down. It's you know it's trying. It's going slower and slower. But once it hits that surface, there's a new equilibrium. They're both trying to establish an equilibrium with each other, which would take that thing that was going very slow, but now suddenly because the equilibrium is so that that molecule is going to speed way up, and that surface is not really going to notice much of a change at all
Yeah,
because it's so much closer to the equilibrium of the two system of the two.
and the surface is made out of billions and billions and billions of atoms that are all at 300 Kelvin, whereas we're talking about one single atom. But if you could somehow prevent it from physically contacting and touching any of those atoms on the wall, then it would just bounce around forever. So that more or less
Bounce around until
gets,
it stopped. Like it would
yeah, because
slowly lose
it would
energy
radiate.
until it.
But ignoring the fact that
Yeah,
it
it'd
would
be a super
radiate,
long time period.
yeah, because ignoring that, it would just keep going like that and bouncing around like a bouncy ball that is really, 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 really bouncy and never loses energy.
Yeah,
But
100% elastic.
yeah, but like what every so often it's going to emit a photon because of physics, other things that are um but that don't really necessarily affect, the issue that we're talking about here. It does
Yeah.
matter. It's when we're talking about clouds of gases that collapse on themselves and form a star eventually, the that energy that's being radiated away is why as the gas compresses, the volume gets smaller, therefore the temperature gets larger and the pressure gets larger. But because it can radiate away, it can get smaller and smaller and smaller until gravity crushes it and starts fusion. But
That's
that's a
why
different
the
topic.
energy
Yeah.
doesn't cause like an explosion and disrupt the whole process. Because if you were trying to normally, if you're trying to concentrate energy into a small point, it would just expand outwards because if the system can't handle the energy, it creates an explosion. Like if you have too much energy in a system, then the system can't handle it. But
Well,
because it's able to
okay,
radiate
like
out.
that you're not necessarily wrong, but what you said doesn't necessarily mean a whole lot. Do you know what
Okay.
I mean?
Yeah.
Like it was a very sort of general statement. I'm not going to say that you're wrong, but we would have to make that idea more precise
Yeah.
before we could. Like yeah, I mean
That's
yeah.
what the energy, it's just clarifying like that there's a release of energy in like the example of a star, like that the star as the volume is
Well, the energy has to be able to escape in other way. Like in order for a gas cloud to compress, the pressure has to decrease when it's small and it blows back up. So why doesn't it just go like bounce, 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 bounce forever like that? The reason it doesn't go bounce, bounce, bounce forever is because over time photons and black body radiation get released, um, and they just leave the system. So it goes bounce, 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 and it compresses more and more and more.
it's kind of like
And
if you
stars take hundreds of thousands at the very least, and almost always tens of millions of years in the typical models in order to do this. So you have that time.
yeah,
But in a laboratory,
you can't do that in like a lifespan
yeah,
like
well,
one.
it sort of depends, and it's certainly
Yeah,
not
example dependent.
happening. My experiment, we start cooling the atoms, and then 600 milliseconds later, they are at approximately like 10 millikelvin, and then a few milliseconds after that, we've gotten
So
them down to less than 10 microkelvin. So we can cool down a gas and do all of this in less than 1 second. And yeah.
that is so just like
But
amazing
yeah, so
science.
so at this point, I'd like to return to the question of,
Yeah.
if you have a gas in a box, if you can prevent the gas from actually touching the walls of the box, or if you can somehow make the walls of the box crazy, crazy cold as well, and you release a single atom in the middle, is it going to get to the top?
Yeah, excluding like any sort of force.
Yeah. It when it hits the bottom, it doesn't get heated up because it's either not touching it or because the walls of the box are very, very cold. Either of those would work.
So then it can't get any higher than its an original starting position.
Exactly. Exactly. So when it comes to the question then of, will a gas always expand to fill the volume of the container, if you just generalize what we just said from, instead of one atom to multiple atoms, you might get, like, if you started with two atoms, and maybe they start at exactly the same height, like they're both going sideways at exactly the same speed. Eventually they're going to bounce around, and because they're going to ricochet, you might eventually get one of them to be up here and the other one to be down here, but they're still going to be like falling, and one of them might even hit the ceiling, but they're never going to both hit the ceiling.
So just curious for curious sake, like say that both of those molecules had a starting point where they were 4/10 of the way, 2/5 of the way up the box.
Uh-huh.
Would the highest possible collision point be that one of those molecules, only one, like you said, only one could get up to max height of 4/5 because you can only go 2/5 plus 2/5? Or could they hit the
Yes.
ceiling? Or
Yeah,
would it be possible?
you're absolutely right. You're absolutely right. So in what you just described, in what you
Because there
just
you had them
described
halfway.
was, yeah. So that's why I'm moving them, so that
Yep.
so this is 40% of H. Okay.
Mhm.
So according to that, this, if it has a mass m and it's at a height of 0.4 times H. So according to typical generally accepted physics, which I believe, and you should too,
Science
the
physics is knowledge. Knowledge.
yeah, so that's particle one and that's particle
Testable.
two, and they're exactly the same. And so the energy of particle one equals 0.4 GH, where G is the acceleration downwards due to whatever force, in this case
Yeah,
it's
we can call it
gravity,
just, yep.
yeah, is pulling it downwards. But if we were on the space station and instead these were charged particles, and you had a uniform electric field, the same math would apply. It just, these numbers, instead of G, it would be different because this is a potential energy. Do you know what, you understand what potential energy is?
But then like
It,
resting energy?
not quite.
Or
It's the energy that a particle has due to its location in a field.
okay, yeah, yep.
So a field is a thing which has a value at every point in space.
So
The electric field has a vector value. It has not only a magnitude, but it also has a direction. So, and at every point in space, if you put an electron there, the electron would move in some direction, or it would stay still. If it stayed still, then the value is 0, and if it moved, then the value would be pointing in the opposite direction, actually, because electrons are negatively charged, but it doesn't matter. That gravity is a scalar field. Okay, so the electric potential is also a scalar field. Gravity is a vector field because it'll point also in a direction. And in this case, it points down. And I lost my train of thought. Sorry.
Would potential energy be like if you have something, like if I have my phone and I pick it up and set it on the table, it's at that table. It took X amount of energy to get that mass up to that height.
Yes.
And now if you knock it off the table and it falls, it turns into kinetic energy. And then that kinetic energy, once it hits the ground, it has a new potential energy where it takes so much energy to get the phone to the floor.
Yes, exactly. And though you can calculate how fast it's going to be going when it hits the floor. So if you have an object, that has a potential energy mgh, and you want to know how fast it's moving after it has fallen from h to 0, then you would set that equal. Damn it. By the way, I apologize. I do swear. It's a thing that I do, and I try and not because I understand. But my sincere apologies.
No worries, man.
Yeah,
no
you are a guy on the internet, so you know. I'm sure you've.
Yeah, I've heard a word or two.
So, what you would do is you would look at this equation.
Thank you.
You would have mgh equal to 1/2 mg squared, and then when you solve for velocity, velocity would be equal to the square root of 2gh. And you could use that to calculate. And g on the surface of Earth is about 9.8 meters per second per second. And so when you multiply that times h, then
say 4 centimeters in a 10 centimeter box for the example up above.
Yes. Oh, that was correct. Yeah. So if you had both of these, then the total energy, and then E2 equals E1, because we decided that they were both starting at the same height, right?
Mm-hmm.
So the total energy equals 0.8 mgh. I put a bar on there because h bar is a thing that I almost always use instead of h because I am a quantum physicist.
Okay.
So normally h is the Planck's constant, but so it would be that. Now that's the total energy from these two particles. If you had either of those particles later, that means that neither of these particles can go higher than that.
Yeah, if one molecule was going to hit the other one from exactly 180 degrees and hit it all energy going exactly straight up in the air, it would only get to the maximum potential height of this of these molecules is 0.8. 0.8.
And in fact, if that were to occur, that collision would have to happen right at the bottom, because all of the potential energy after that collision would be in the kinetic energy of one of the particles. So one of the particles has to stay at the bottom, and then the other particle would be able to make it all the way up to about here, but no higher.
Okay.
So now we've generalized from one particle to two particles, and we've seen that still, if the box is high enough, or if the temperature is cold enough, because the temperature determines how fast they're moving.
You would have to
Right?
super chill the walls.
Yeah, yeah, but we're imagining that the walls don't interact with the atom, and there are ways that you can do this. The in the 70s, spin polarized hydrogen was cooled down in a box, and the way they kept it from interacting with the walls was they put superfluid liquid helium inside the walls, and superfluid helium is a very weird behaving substance
Isn't it
that
frictionless?
yeah, and it climbs up walls on its own, which is it's weird. It's a weird thing. Um, it's counterintuitive and it's strange, but it also it doesn't interact with things. So when the hydrogen would try and hit the wall, it would hit the helium, but the helium it doesn't really interact with. It just bounces off. So they were able to basically make like a force field out of liquid helium.
And suspend this hydrogen molecule in it.
Yeah. The way we do it is instead by using we instead use the radiation pressure from light. So light, the photons, each individual photon has a little bit of momentum. So when the atoms absorb them, they get pushed back a little bit. And
wow, for something massless like light?
Yeah, it's interesting. The light does actually have momentum. It is not due to its mass. It's due to its wavelength. So the momentum for a photon, so P is the symbol that we generally use for momentum in physics, and gamma is the Greek letter that we typically use for photons in physics as well. And so the momentum of a
Photon.
Of a photon, yes, thank you, is equal to the reduced Planck's constant times 2 pi over the wavelength. So a very, very short wavelength photon has a lot of momentum, and a very, very long wavelength photon has low momentum. And
because there's a lot more energy in a short wavelength light than in a long wavelength light.
Yeah,
higher energy, so that would.
And it's actually when you were talking about how when you push energy into a smaller and smaller amount of place, it's harder and harder. To some extent, a similar intuition can be applied in that same situation. When you make it when you make a quantum mechanical object into a really, really small space, but there's still a lot of curvature, and photons have, they oscillate, right? Then squishing that curvature into a small amount of space increases the energy, but that's neither here nor there. Photons have momentum is the sort of takeaway from that. So if you have an atom, suppose the atom can only move up and down. Like we live in a one-dimensional universe. There are no other dimensions, and it goes up and then it falls back down. But when it falls back down, it gets hit by another photon, and then it'll go back up, and it'll just like keep on doing that. It also has to release that photon, unless it just keeps on absorbing photons forever. But
it'd be a really high energy molecule.
Yeah.
After a little bit of time.
Yeah. So the way we use lasers in the lab to cool down atoms is we shoot a laser this way, and 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 we do it so that we bring the frequency of the light just below what the atom needs to absorb a photon. And then because of the Doppler effect, when the atom is going towards a laser beam, because of the Doppler effect, that laser beam looks like a higher frequency and it can absorb the atom. So at that spot in the middle, the atoms are always going against one of the lasers.
You're tricking molecules here, getting them to think that the energy is different than what it is.
Yeah, and so it's like right in the middle. There's suddenly they walk into a room where no matter where they try and go, when they get to when they try and leave, they open the door and a gust of wind blows them back into the room. But it only happens when they're going in that direction. So if they're always pushed backwards, eventually they're going to stop moving forwards, and they're just going to be stopped.
But then, because once it's moving backwards, it's moving essentially
it's not getting
forward
pushed
to
anymore.
the other laser.
Yeah, exactly, because the one behind it now is pushing it forward. Exactly.
So yeah, you suspend it in one spot.
Yeah, so you trap it in one spot.
That is so cool. That is so like spectacular. Oh
it's incredibly cool. It is in fact ultra cool. But
he did it. He did it.
Being able to do that and slow down atoms with laser beams in that way was one of the main reasons for the awarding of the Nobel Prize in Physics in 1997 to Claude Cohen-Tanuji, which I'm sure I butchered the name. My apologies. Stephen Chu and Bill Phillips, and they got the Nobel Prize in 1997 because of various things they did in using the fact that when you shine light against the atom, it can slow it down and make it very, 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 very cold.
And this leads to us being able to just real briefly want to touch on like something like this, like being able to do this with a molecule. This leads to us being able to learn about like quantum states.
Yes.
Okay.
Yes. Yeah. Okay. So like the title of my dissertation was implosions as a probe for fluctuations in Bose-Einstein condensates. And we use laser cooling and a bunch of stuff in order to so we have a chamber, we have a vacuum chamber, and now inside of that vacuum chamber we have all those lasers.
And so I just want to clarify too, so this is in the with the first question here of, does a gas always occupy the fullness of the container?
Yeah.
It is, I mean, it depends on the energy of the walls and of the molecule, but and the collisions that are available to be had by the molecules. But there are instances like here was shown that a gas molecule is not always able to, if the energy required to get to the ceiling is not within the system, it cannot get to the ceiling.
Absolutely.
Okay.
Wonderful. I honestly like if like that's where that is one of the 2 points that I wanted to like sort of communicate. And to some extent, as I said, it includes the second point, right? Because now up here you could have a vacuum, and down here you can have a gas.
You would have a vacuum. If there's no particles, that would be a vacuum as to what we call it. Like, you know, very low dense particle density.
Yes, and I appreciate that you understand that, because so like in our experiment, the gas pressure in the middle there, where all the lasers are pointing against each other. Let me get some blue marker here, because we use blue lasers. It's fun. Where's the blue marker? Come on.
Not green lasers are very.
Yeah, we use red and we use red lasers and for the second stage, and blue lasers for the first stage.
Yo,
I don't know where they are.
While you're finding that, I'm gonna cut my lights real quick. I just want to do this real
fast.
Don't know why.
Yeah. So.
Whoops. Oh snap! I gotta put the other battery in. Never mind. Dang it! I was gonna shine a laser through this. Lasers are literally, you've redefined the coolness of lasers.
Well, lasers are a whole nother thing. Lasers, technically, you can define a temperature for the photons like inside of it, and you can define it in a sensible way to give negative infinity. Very different definition of temperature, though. but still valid, but it no longer means average kinetic energy. It's a totally different thing.
Yeah. Okay.
So in our chamber, we blast them, and we can get we can get a cloud of atoms to sit right there. And over here, the pressure is small. it's small. It's on the order of like 10 to the negative 11 torr, and I actually can't remember what that is in units of atmospheres. I think 1 torr is about 1 atmosphere, but I can't actually remember.
1 torr. I think
but
1 torr, 760 mg.
Yeah. Because 760 millimeters of mercury is about an atmosphere. Or something, right?
mmHg.
Yeah. Exactly.
And I think for context, I think they say like deep outer space is 10 to the negative 17.
Deep, that would be like interstellar space.
Yeah.
So like between galaxies, you have a particle density of like 1 molecule or atom per cubic meter.
In molecule.
Deep, yeah, right. Yeah. but
so in your lab, you are getting a 10 to the negative 11 torr area around this cloud.
Around there, yeah. And then there, I know what the particle density is. The particle density is about 10 to the 10 atoms per cubic centimeter, I believe. So
how big of a
I actually don't know what that is in torr. I'd have to do the calculation with the volume, and also because the gas is most dense right at the center, and then it becomes slightly less dense at the edge, because it's not it's in equilibrium,
for our day-to-day, where like the number 100, I mean, it's all in context, but like 100, 1000, 1 million, which 10 to the 6 is a million. And so you're dealing with roughly like a large amount of molecules. I mean, it's a very small cloud, but it's not
it's visible by the eye. So in the first stage of the MOT, it's visible. You can see it. It's a bright glowing blue ball. Let me see if I have a picture just on my phone ready to go. I might have one.
Ooh.
Come on.
Man, that's fascinating to think. Like that's a suspension of gas molecules in a very strong, probably one of the strongest vacuums that we are able to achieve with our technology. And that is held together molecules.
Yeah.
If you got a picture, you please.
I don't have one. I don't have one just sitting here handy. I have.
Yeah, if there's no, we'll try to get one. Michael, can I say that? Can we try to get one at some point here, just for reference?
We can put it. I'll send you a picture, and we can link it in the description.
Yes. Okay. Because that's like.
But
that's awesome. It's visible, that you can actually see.
It's about a centimeter. It's like that big. Because the lasers are about that big. So because if your laser is that big around, then the spot in the middle where they're all intersecting is going to be about that much, but in volume.
And it'd be washed out by the laser too. Like if it's visible light, like you got to use a small diameter beam to be able to
relatively relatively small. But if it's too small, then that volume is going to be too, like, you get more atoms if it's a larger area. there's a lot of complicated stuff that goes on, but it's a bright blue ball that glows and is very impressive, and everybody who ever sees it is like, that's really cool.
Yeah, that is so basically you have, I mean, in this example, in this example here, and with the example of the height of a container and the starting position of molecules, showing that they wouldn't reach it to the top, you have shown that there are circumstances where you can have both gases not getting to the top of a container, filling a container, creating a vacuum at the top of that container. And you have also shown that there are that you can get molecules of gas surrounded by a vacuum, but the molecules of gas do not take the shape of that container. They're not trying to expand out. They are being held and cradled
Well, they're
in that
trying
position.
to. They're trying to, but when they expand, if they expand out, there is another thing that's going on here that also, because once they go still, they're going to fall down, but they're only going to start absorbing the light going upward if they're going a certain speed down. So if they go slow enough, they would eventually fall down.
Do you use
Now,
it?
we also have magnetic fields that are also on. The physics and the math for that is more complicated. But if gravity wasn't a thing, this would cause a local density maximum that would persist.
So
So,
do you have
yes,
just
but I just
for,
want to be open about that.
yeah, and just curious for like the apparatus setup instance, or for the sake of the apparatus, like does the downward beam and maybe even the do the vertical beams have to be maybe like a slightly different diameter compared to the side beams to compensate to for the downward acceleration?
So interestingly, in our apparatus, we actually we don't have the beams going like this and like this. We have them going like this, and like this,
Okay.
or rather like that and like that, because
X marks the
and the way
spot.
you do that is you just you shine one and then you have a mirror
Yeah.
just bounce it back.
Okay.
But yes, it actually means that we need to put a little bit more power or intensity into those beams than the beam going along this direction, because
Okay.
those beams have to hold it up against gravity, whereas this beam doesn't have to hold it up against gravity. So yes, you're exactly right.
That is, gosh, yo, I can't wait to see that. Like,
Yeah, dude.
oh my
It,
gosh, that is so neat.
yeah.
Okay, so I think we've that actually that was kind of succinct how those that you covered both of those, because those are questions people have and people speculate on. And so there are conditions that are possible where you get the results of gas not taking the full shape of the container, and where you get gas next to a vacuum without a container, separating them without a barrier. I think that the question that would then be asked is, these conditions, are they what we experience in the natural world, in the scale that we're talking about, or in the
Yep.
conditions that we are talking about? Is there overlap?
That's an excellent question. And that, you want to do the math? We can just do the math right
You
now.
can do the math if you could just explain it while you're doing it.
Yeah, absolutely. Okay. So let's choose can you look up what the mass of a nitrogen molecule is? Just like go to Wolfram Alpha, or
You're talking a mole of
a
nitrogen?
single molecule, because the gravity on a single molecule is only going to be one if it's a mole, you're gonna have a factor of m. It's actually going to drop out. So
Yeah.
but
Because like I know you can take a mole, like I think a mole of nitrogen is 14.
Let's say it's a kilogram.
Yeah, it's 14,
not a kilogram.
14
it's gonna
grams.
Be 14
in,
grams.
And then you divide by 6.022
times 2 because
10⁻23rd.
molecular nitrogen is typically N2, not N1.
Oh yeah, N2. Right? Okay, so 28.
Yeah. So let's say you have a
6.
mole of non-interacting, whatever. So we get the mass of the nitrogen. Again, it actually doesn't matter. And let's say that we're talking about a chunk of nitrogen out in the atmosphere, and it is, say, 300 Kelvin. That's what the temperature is. Okay? Mm-hmm. So mass equals that and that. Now, how fast is a typical molecule going to be going at that? That's a capital K. At that temperature. Now, I'm just going to give you the formula. You can derive this, but it does fundamentally come from statistical mechanics and equipotation theorem, and we can talk about those. But hopefully, right now, you'll just kind of believe me that the velocity, you're good. The typical velocity v, is going to be equal to the square root of kt over m, where k equals 1.223 times 1.28 times 10 to the negative 23. It's the Boltzmann constant. Let's look it up. Boltzmann's constant, which was defined.
Yeah, sorry, I couldn't find the weight of an N2, the mass of an N2 molecule.
We're also the reason it's going to drop out is because of an approximation that I'm going to make later, which you are going to call me on for being incorrect, and you're going to be right, but it's going to be pretty close. What was it? 1.38 times 10 to the negative, or is it times 10 to the positive? Times 10 to the negative 38 times 10 to the negative 23 joules per Kelvin. So if so that's the velocity, and we're going to set that equal. We're going to figure out the kinetic energy. So then the kinetic energy is going to be Ke equals 1/2 mv squared equals Kt over 2. You've seen that the mass has dropped out because when we multiply v squared, we get an m in the downstairs, and that cancels this m. Mm-hmm. So you agree that this is equal to the kinetic energy. So that's how much energy this molecule has just because it's existing in the atmosphere and it's moving around. Okay?
In any random particular N2 molecule, that's its kinetic energy.
In fact, it's actually it's any molecule in the air because the mass dropped out. The only thing that specified we were talking about nitrogen in this case was the mass. Yeah. But yes. So that's the kinetic energy. Now, as the thing goes up and up and up and up and up, if it starts at some level that we're just going to call 0, okay?
Wait, can I just real quick? So regardless of mass, all molecules of gas are moving at the same kinetic energy?
They all have the same average kinetic energy because that's
which
what
would make sense.
That's what temperature is.
Okay.
Yes. They do not have the exact same one. There's a distribution. Some of them are moving fast, some of them are moving slow, some of them are moving that way, some of them are moving that way. They're all all bouncing around. A typical molecule only travels, I think, a few dozen nanometers before it hits another one.
Very small.
It doesn't go very far at like sea level. When you go up higher and higher and higher, and as I presume you agree, because this is very, I think, well agreed upon, air gets thinner as you go up. The pressure does get lower.
I think it's
right?
we can measure that.
Yes, exactly. Exactly. And that's the one that a lot of people like to do. Well, if it keeps on getting smaller as you go up, that means it has to go to zero. Not technically. You can have a limit that gets closer and closer to a value that isn't zero, but is always getting smaller. Like, that works.
What is it? An asymptote, right?
Yeah, exactly. It just because something is always getting smaller doesn't mean it's asymptotically approaching zero or negative infinity. But in this case, as you go higher and higher and higher up, if gravity is mostly the same strength here as it is up there, and that's the part that you're calling me out on, because you know that's not true and I know that's not true.
Yeah, it would get weak.
It does get weaker, but for the thickness of the atmosphere is about that thick over a distance from the center of the Earth that's like that big.
Yeah, it's so like a couple hundred miles over 4,000.
Yeah,
over a radius of, or a diameter of 4,000 miles.
I think it is radius. I think it is, but yeah, so, exactly. So gravity is mostly constant over that.
Yes, despite getting weaker at a squared rate.
Yeah, it does get weaker, and you can include that. Then you have to do calculus to sort of, you have to do an integral, and you have to, the math gets a little bit trickier, but the physics is all the same, and that is why you can go fast enough to escape the Earth's gravity entirely, because eventually you get out far enough that, yeah, you're always getting pushed back, but as we just discussed, you can asymptotically be slowing down and still never stop and turn around. You can keep slowing down to a velocity of 5 miles an hour away from Earth. If your final velocity gets closer and closer to 5 miles an hour away from Earth, you're still always moving away from Earth. You're never
at a speed.
You're never
so eventually you're going to escape, which is I think it's called atmospheric loss.
Yeah,
is where like the tops are blowing off.
So here we have the energy of a molecule. So we have K times T times 2. So we have 1.38 times 10 to the negative 23 joules per Kelvin. That's what Boltzmann's constant K is equal to, times 300 Kelvin. That's what the temperature of our gas is, divided by 2, equals, well, I'm going to call that 1 point, I'm going to call this 1. Okay? Are you okay with that?
Fine by me.
Yeah. So we're going to call that 1, and then that's 300. So 300 times 1 times 10 to the negative 23 divided by 2 equals, actually, yeah, equals 1.5 times 10
negative 25.
Negative 21. Because this is 10. This is 3 times 10 to the power of 2 plus times 1 times 10 to the power of negative 23. The power
makes it a bigger number, so a smaller negative exponent.
Exactly.
Okay,
yep. So we could do 3 times 10 up 2 Kelvin. That would be another way that we could write it.
Yep.
So that's going to be equal times 1.5 times 10 to the negative 21 joules. Okay? So we have 1.5 times 10 to the negative 21 joules. Where did I? There we go. And that's going to be equal to, we're going to set that equal to, we want to know how high that molecule can go before it stops going up and starts falling back down, which we agreed would happen, right?
It is, yeah, it's
We
possible.
would agree
Okay.
if gravity did not get weaker as it went up, which over this, if we get a number here, by the way, that's like 18 trillion miles, then we're going to be like, okay, yeah, but we know that gravity isn't constant over 18 trillion miles.
Yeah,
Okay.
that'd be a lot.
So if I get a number here though that's less than 1,000, it's going to be off, but it's not going to be off by more than we can do the math, and I'm willing to do that. I probably can't necessarily do it live, but I could show my work, and I could probably prove it to your heart's content. You've been incredibly astute and on top of following this. You're doing very well. This conversation is going like my wildest dreams. Fantastic, wonderful.
Yeah.
So
Man.
that we need to set equal to the potential energy due to a constant gravitational field for this approximation, and that is equal to m times g times h. And now we do need to know the mass of a single molecule, because this was the kinetic energy for a single atom or molecule rather, because the m here is for a single one. Okay. Yeah. If we were talking about a mole, the same calculation would hold. It would just be that this would be true for every individual one, and we would still end up, the mass here would still end up being just the mass of a single atom.
Okay.
That might have, I realized I said that, and it confused me coming out of my mouth.
Say that one more. Could you say that one more time?
So because this energy balance, the energy balance is occurring for each individual atom, and they might be bouncing off each other, but on the average,
you're going towards that equilibrium.
Yeah, exactly. So we can imagine what would happen for one atom, and then we know that when we add a whole bunch of them together, some of them are going to be going faster and therefore be able to go higher, but some of them aren't going to. But that means that some of them aren't going to be able to go as high. So, so now our equation is kinetic.
Just to cycle it back. So, like in that example, how we talked about the 0.4 and the 0.4 starting points, for that one to get to 0.8. The other one has to be at 0 because you only have a total of 0.8 to work with.
Exactly. And on average, the typical thing that you're going to see is that particle 1 is going to be roughly at around 0.4. That's going to be roughly the highest it gets on any sort of random trip. And particle 2 is also going to be at 0.4. There's nothing to break that symmetry. They're identical. So, yeah. So now we have this, and the mass of, let's look it up. Let me just pull up Wolfram alpha really quick here. But I mean, I can't remember exactly what the mass of a proton is off the top of my head, but mass of Gen. Okay, so nitrogen's atomic mass times 2 is equal to 4.7 times 10. Okay, we already did this calculation, so I'm going to erase this one. Do you like my whiteboard?
Yeah, it's really nice. I like the stand and everything. You use it
Yeah.
very well too. You use up all the space and everything. It's
Yeah,
very
right.
efficient.
I I'm a physicist, and like when you said that you had taken astronomy, I was like, oh, that means I'm going to be able to do math.
Yeah.
Because yeah,
And
that's
you turn
also
it
a
into
thing.
an infinite whiteboard. You just work your way down, and then once you get to that bottom, you restart it at the top. And just...
My dream. Oh my god, my favorite. Sorry, my favorite lecture halls in the universities that I have been to. I got my PhD at University of Colorado, and some of the lecture halls had like 3 blackboards, or some of them had whiteboards, and each one of those had 3 layers that slid up and down, so you could cover a full whiteboard and then just push that one up, and then beneath it there was an entirely fresh whiteboard. And when you were done with that, you could maybe it was only 2, I don't know. You could push that one up, so you could have this, and then just shift it up, and there'd be a full. It was amazing. I want to get one so
Just like
bad.
the teachers got all that space to work with, and the students are just sitting there like, wait a minute, I only got this one notebook. Like, how am I supposed to write this out?
Well, yeah. I mean, the way you're supposed to do it is you pull out your phone and you take a picture of it.
There you go. No, isn't technology amazing?
I mean, look at the conversation we're having, man.
Very true.
Right? Like
face to face, the way to be, and this is pretty much almost. This is second best. Second best to face
right?
to face is right here.
And I mean, it's been, man, like if COVID had happened 10 years earlier, it would have been rough, because we wouldn't have been able to just like kind of pivot so many things to. We don't need to get into that.
Lot to be able to like zoom and everything is a really
right?
An amazing thing, and it kept some of the social aspect to it. Like there are, I don't know how much I can talk on that on like this platform, but like there's like there have been some social ramifications from like kids going 70% of their life seeing people in masks and everything. So it's good that helped keep a lot, like at least some sort of social face-to-face type of interaction.
I agree. I think it's not as good as good old-fashioned communication. I've been seeing a therapist for various depression and anxiety things that really I ran into I hit some hardcore burnout in late 2019 in grad school. I was very, very depressed, and it was really rough. And I've been in therapy since then.
Are you doing better?
I'm doing so much better.
Excellent.
I'm doing better than I ever have in my entire life. I am
very good to hear.
I am happier. I am happier than I have ever been in my whole life. It's amazing.
Good, man. Good on you.
A good,
way to go,
effective, qualified, competent psychotherapist was an incredibly important part of that. Incredibly important. It's amazing. And we've actually been talking, one of the things that we've been discussing in recent months has been my social anxiety, which I actually have a fair amount of social anxiety, which may not necessarily come across as obvious. Right?
Yeah, handle yourself well.
Yeah. It's like I don't really have many friends that I like around where I live. Like I moved out here last August and September. I got my PhD. I defended last June, so it's pretty recent. It was June. Yeah, it was June. I've been a doctor for more than a year. Holy crap.
Time flies, but that's a quick turnaround too. That's speedy.
Well, it took me 8 years. I spent 8 years in graduate school. That's not speedy.
You graduate though, find a job. I'll say this: you are moving a lot quicker than the atoms that you slow down.
Yes. But I was bringing that up because, yeah, no, my therapist has been like, we've been talking, and she's begun to sort of understand that I do have a social life. It's just that it's mostly online. Like the show I host with Maya. I don't know if you saw any of them at all. But like on Sunday evenings, this past Sunday was one of the first in a while that we missed. And like Mark Reed, who you've talked with, another friend of mine. So it's like I have like a community, but it's not the same as an in-person interaction and relationship, which he keeps on telling me, and I keep on mostly
That's
ignoring.
I think I think to add to that, like having people like I live with one of my best friends and easily, and it's so amazing to live here. And like I think like having people that like online that you can talk to as well. I think what would be really cool, you get all these people that you like talking with online and get together in person. And then you do like
Yeah,
that would be the type of stuff. Even if you bring them up to your friends that you hang out with like IRL or whatever, like
yeah,
like it's the networking and stuff. But I think like that stuff is so it changes the dynamic of
yep,
interaction when you're like in person with people as opposed
totally.
to. But this is still, I mean, for what we have the ability to do this, and we
It's
can do a
amazing.
lot with it. So
Yeah.
it's incredible. You are mathing to me right now
Yeah.
through the
And
interweb.
yeah, so now that we have that, we what was it? It was 4.7 times 10 to the negative I should probably do it in kilograms because that's the standard international unit. 10 to the negative 26
Go metric America.
kilogram. Yeah. I'm a physicist. I'm an American physicist. It's so painful because
Yeah.
I think into this weirdest combination of metric and imperial, because like in my day-to-day life, I think of speeds in miles per hour. But
Yeah, right.
in the lab, I think of speeds in terms of meters per second. And
Yeah, and
I
metric,
legit,
it's like quickly divide by 5,280 and multiply by 7/8. Go.
yeah, it's like
It's
metric, just
10, 10
multiply by
times
10,
10, divide
multiply
by
by a
10.
different factor of 10.
Yeah.
It's very easy,
Oh
yes.
my.
Yeah, man, when people, because I've seen like occasionally you'll get like just people who don't know what they're talking about get on Twitter and be like, metric system is communist, and I'm like, oh my, no, it's just for lazy people,
It's a
and
number system.
we all
It's
want to be
for,
lazy.
it's for, ooh, did the scientists hear that? It's just for lazy people. Ooh, no, it is. It's simplifying a difficult subject and making it more graspable by
Yeah,
using pens rather than
there's no
uh
reason to make it harder than it has to be, right? Like
no, no,
there's
why
no
would you?
reason.
Less people are gonna get it, and you're gonna get less people interested or in these conversations the harder things are. Like the
Yeah.
more you can, like Mike, I think you're doing great at like breaking this down, showing it step by step, laying it out. You've got the diagrams, you're drawing things out. You have the math to show it. It's
Hmm.
this like this is why he's a teacher, y'all. That's why he works in like he knows that like
Yep.
this
So now we're gonna solve for the
methodology.
height. We're gonna solve for the height that molecule can go.
Mhm.
Okay. And to do that, so we have 1.5 times 10 to the negative 21 joules. That's in units of energy. It's in units of joules. And a joule is a kilogram times a meter per second squared. So when we divide both sides, we're going to divide by 4.7 times. I'm just going to use the E notation because it's easier. You know what? I'm going to change this to 5 because I'm lazy. 5e negative 26. And G equals 9.8 meters per second squared. And time, so, and we're going to round that to 10. So times 10. And so now this number 1.5 times 10 to the negative 21 divided by 5 times 10 to the negative 25 if we incorporate this factor of 10.
Mhm.
That will be equal to, let's do the power of 10 first. We have negative 21 over negative 5, negative 25. So negative 5 is going to be negative 4 is going to be the power on the bottom. Where is my, oh, there it is. So that would be equal to, so it's 1.5 over 5 e negative
Negative
4. Yeah. And what's 1.5 divided by 5? It's 0.3.
Yeah, 0.3. 30%. Yeah, 0.3.
0.3. And if we move this upstairs, then that's times 10 to the positive 4. Okay? Which equals 3,000 meters. So
That's 3 kilometers.
yeah, that's 3 kilometers.
And
Now,
the atmosphere goes up.
It goes higher than that.
Yeah.
Right?
Yep.
But what we have talked about here is this is how high you would expect the typical molecule of nitrogen. That's how high you would expect the typical molecule of nitrogen to go if you released it at normal room temperature at sea level, and it had this amount of velocity, which is just the average velocity along any given direction. Okay. The average magnitude of the average actual velocity is 0 because they're a particle going this way and a particle going this way cancel each other out. But the average speed is going to be this. It's technically, velocity is a vector, so technically this is the typical magnitude, because so those molecules, if it was bouncing around, that molecule would be able to make it up 3 kilometers into the air before it would turn around and fall back down. Now, I'm sure that you know that the temperature actually increases at certain layers of the atmosphere, right?
Yep.
Like the thermosphere and stuff, it gets hotter and hotter and hotter. There are a lot of complex reasons for that, okay? And yes, that changes this calculation. And yeah, when it gets up there, it suddenly, now you have to imagine, like, okay, well, now it's at some temperature here. How much higher can it go? Some of these atoms are going to be able to escape. The lighter they are, like hydrogen and helium, the further they're going to be able to go. The heavier they are, like krypton and radon, they're not going to be able to go up as high because you're dividing by a bigger number here. This number suddenly might go up by a factor of 100.
Which would knock it down to 300 meters.
Yeah,
So,
exactly.
Whereas,
yeah. So this is like an order of magnitude, very roughly, of roughly how thick an atmosphere might be. Now,
because say you have hydrogen instead of nitrogen, which is just say hypothetically it adds a factor of 10. So now instead of 3,000 meters, you can go 30,000 meters.
It'd be about a factor of 14 because the mass. Oh, yeah, it would, because the mass of a hydrogen molecule is about 14 times lighter than a nitrogen molecule because it only has 1 proton as opposed to 14 protons and 14 neutrons. It has 2 protons as opposed to 14 protons and 14 neutrons in a nitrogen molecule. Yes. But yes, go on.
So that would be you could with this approximation you could have a lighter molecule, and yeah, like if you got 3,000 for nitrogen, if radon got you 300 and hydrogen got you 30,000, that's all within mathematically that is within the range of the atmosphere.
Yeah, it's not crazy, right? Like
Yes,
it. You,
it's not that
somebody
50
yeah
billion
somebody
number.
somebody could interpret what I am saying, and they would be quote mining me.
Please don't do that.
Yeah, thank you. I 100%. um and dude, at this point I would be shocked if you did that, and if you did do it I'd be like, oh, he genuinely thinks that I agree with him on this, let me clarify that.
And if that ever happened, you always
Yeah,
always
yeah,
clarify things. But yeah,
yeah, yeah.
I don't want to
But
misrepresent. I
so what's the radius of Earth? Radius of Earth.
think it's 39. What is it, 3950?
It's roughly 6,000 6,400 kilometers.
Oh yeah,
Okay,
sorry, Calvin Imperial System.
and this is 3 kilometers. Okay, so
Mhm.
that means that we're talking about, if this is the Earth, okay, it's a sweet Earth, it's chilling. Um, then we're talking about a minuscule difference, which means that this approximation is like pretty good
Mhm. Can I
because
ask you about a variable in there?
yeah,
The m you have g, which
yes,
is representing like the downward acceleration.
yes.
Um, Curious as to on a molecular level, they say that that electromagnetism is like 30 30 orders of magnitude, 20, I think it's like 26 to 36 orders of magnitude stronger than gravity.
Honestly, that sounds plausible. I actually don't know the number. It's a lot. It's lots.
Okay.
So yeah.
So is there a way to isolate, like, I guess how do you distinguish between um like the EM versus gravity
Mm.
to know
So
which thing might be holding something in?
yeah. So for one thing, um, nitrogen molecules in the atmosphere are electrically neutral, right?
Yes. Yeah, and
So they
two.
don't have a net charge. So the fact that there is an electric field, around the Earth, which, by the way, this is a point that flat earthers win on, um, more often than they lose on it, in my opinion, because there is a roughly 100 volt per meter differential, right? And when you tell that to a physicist, I tell that to my colleagues at the lab. I'm like, by the way, did you know that if you just like go out into like the woods, there's like 100 volt per meter electric field. They're always like, wait, what? Really?
Because you could get like shocked if you had like a really long wire or something that went several meters into the air. It could generate a lot of
Well,
electrostatic potential, right?
but it wouldn't, because inside a conductor, all of the electrons just immediately move to zero that out. So inside the conductor, there aren't any.
Okay.
But the actual potential, they do that because they are getting pushed. So there is a field, but a neutral particle isn't going to feel that electric force in in the way that it would feel a gravitational force, because it doesn't have a net charge. There are more complicated things called Stark shifts. There's the DC Stark shift and the AC Stark shift, that occur and talk about how the internal energy levels of a atom or molecule shift when you apply an electric field, those are well beyond the scope of this conversation. They are also irrelevant to the scale of this problem. Those are fractionally tiny effects. We use them in the lab, not the Stark effect, which is for electric field, but we actually can use the Zeeman effect, which is the same idea, but for a magnetic field. So these a little atom generally can and does, a lot of them do, behave like little magnets. They've got a little itty bitty magnetic field. It's real tiny. It's real tiny. And what that means is that when it's aligned with the magnetic field, it has low energy, and when it's aligned against it, it has higher energy. It's possible that I have that backwards for some atoms. That's the difference between paramagnetic and diamagnetic. I just want to, like, there are subtleties here, but generally, and like but it actually, if you have an atom that's against the magnetic field, then it's going to want to go to an area where the magnetic field is less intense, because then the fact that it's going against the field is not so much of a problem. It can minimize its energy, and it sort of gets pushed to an area where the magnetic field is a minimum. This is all becoming much more complicated, and I'm referring to things that I do not have the time to explain in detail here. But the thing is, it won't just flip. And the reason it won't just flip is, in order to do that, it would need to absorb a photon, and the probability of, or release a photon, and the probability of doing that is very low for quantum mechanical reasons. Again, that I can't necessarily go into. So they are electrically neutral, so you don't really have much of a direct electric force that's keeping them up. And magnetically, they are very, 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 very small. And also, they do have enough. They're bouncing. They are hitting each other, so they're going to be able to flip to whichever magnetic field state is fine. So they don't actually they don't have a well-defined magnetic field state.
And they're easily able to find that the magnetic.
Yeah,
field.
They just, every time they hit something, they're at such high energy. Like, you have to get down well below like a Kelvin. You have to get to ultra cold. You have to get to like my level of cold, I believe, before it gets down to the level where those effects are even noticeable. The electric effect, if you had like an extra electron on all of these atoms, then it would be enormous, and it would just get pushed around according to whatever the local electric field is, and that's how you get lightning.
But most molecules in our atmosphere are not ions. They are
exactly. So they don't really feel those things. What they're feeling is, occasionally they're feeling whatever is happening when they hit another atom, which is fundamentally due to the electromagnetic force. By the way, the term force, when we talk about the four fundamental forces, we don't mean it in the same way that we mean like F equals mass times acceleration. We mean it in like a phenomenon or an interaction. It's slightly different, so you don't want to necessarily confuse them exactly. But that's just sort of an aside. So as pertains to your question, how do we distinguish between the two? If there is some other phenomenon, some other force that we are unaware of that is interacting with these particles, then that would be one way in which we could be fooled. We have no evidence for that yet. So and we think we understand that they aren't ions, and we think we understand that they aren't
There's
ultra
not an
cold
extra
and spin
electron.
polarized, so that they don't have well-defined magnetic states. So therefore, the only game left in town is gravity.
Okay. Which would be that would give you that downward acceleration.
Yeah.
Which is what we observe that things do fall at a rate.
Yep.
Um at an average rate. Um hmm, okay. And that so hmm, with molecules, because like one of the things that I um am curious about is like if we have a well being carved out by the earth, and it's like this, and the earth is in here, and then there are molecules up here, and they're also creating a pocket in like, well, I guess going into like space-time fabric would be a little bit
Yeah.
um
Also, that's another thing. It is technically true. It is technically true that gravity is the curvature of space-time, and it's not a force. That was why one of the reasons I gave the thing about the force. It's sort of a general concept for like an interaction or an effect.
interactions.
Yeah, or an effect. It's a more broad term. So like Sean Carroll. If Sean Carroll, fantastic science communicator. He has a series, The Biggest Ideas in the Universe, which I think is a little bit presumptuous, but even as a physicist, he's a theoretical physicist, not an experimentalist. But I highly recommend just about everything that he has to say. Um, I
My
like to
dad's a
say,
big fan of him.
yeah, he's a very good communicator, and he talks about how like when he learned general relativity, like he got like all hot and bothered about saying that gravity wasn't a force for a while, and then like later on in life he realized like he was just being obnoxious. So yeah, I
And
think
that
that when people want to split that hair too much, they're missing the point.
yeah, it's to help describe and help with the conversation
Yeah, and
is
it
the
just the
way
word
that the
force has
word.
a different definition than what your typical like we use so many words that have different definitions. How many different
You
definitions
can
does
be
the
a
word
force on
love
a
have?
field. If you're playing like like football, and you're a running back, and you're a force if you're able to like get
Yeah,
through the
right.
line. And there's a lot of definitions to the
Exactly.
word.
How many
Uh,
I mean, how many definitions of love do we have?
Not enough, because we need
I
more of that in
It's a
the
good
world.
answer. That's a good answer.
Um,
But
there's
a
plenty.
lot though.
Yeah, not yeah, not plenty. It'd be a lot. And
Mhm.
yeah, one day there'll be enough definitions for that, for love. Um, I did want to. I might have to wrap up here. And I do have to think about that leaving that only leaves gravity as a possible influence on the molecule, because that kind of had my mind going. Well, you showed a lot. You showed that things are within range mathematically to what we observe, what we measure, and clarified a lot as well. And so I will say that I think this was really kind of what I had been looking for as well. So I am really I want to just say again, I really am thankful for your you being on here. Um, if you I guess if I could, are you cool with if we could wrap it up here? We could if
Yeah.
then if
By the
you want.
way,
Yeah.
given how well this has gone, I for one would love to do more of these.
We can make that happen. We can
because
definitely make that happen.
I feel like this is, I feel like in this conversation we have, there has been more effective communication between a flat earther and a round earther than in literally any conversation I have ever seen on the internet before. I don't know if that's true for you, but for me it is true.
That's good. That means communication is on full open channel, because that's and I think that I personally
Yeah.
am of I think that that's we communicate. I think people should. It could avoid a lot of problems. I did want to ask you if you could, and I'll let you. This will be my last words here, and then we'll sign off. But if you want to, I did want to ask you if you could mention your take on what is science to you. What is, if you have any philosophy of science, your theoretical versus experimental, computational. If you want to mention your take on that, and then maybe
Yes.
if you want to go into just an ethical thing or moral thing of science, your take on any relation between those, and then if you want to close out with anything, please feel free to do so.
Yeah, sorry. I ran into the other room because there is a particular book that I like to recommend to people and I can't find it. I probably lent it to somebody and don't remember who has it. This is another good one though. Oh wait, no, that's not the right one. Um there so what is science? It's a big question. I think science is about the way I think science happens is that you come up with a model and an idea, and then you compare that idea to reality based on experiment, based on prior experiments, based on collection of data. You can, if somebody observed the sun rising every day and setting every day, then they would come up with a model and say, I predict it's going to rise at this time tomorrow. And that 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 just alone is a scientific prediction. You're thinking about the world, you're creating a model, and then you're evaluating that against reality in some way. Science should be falsifiable. There should be a way to test the predictions such that if you are in fact wrong, you'll be able to find that out. If you say the sun is going to rise at 5 a.m. tomorrow, that is a falsifiable prediction because it could rise at some other time. So science should be falsifiable. Science is also about explanations. You're trying to explain things. That's sort of what the modeling is. And it's about conjecture and revision. Because your model, maybe the sun doesn't rise at 5 a.m., maybe it rises at 5:02. That's if everybody else is guessing 5:15 and you're guessing 5:02 and and you're guessing 5 o'clock and it actually rises at 5, everybody got it wrong, but you got it less wrong, right? So I think that the debates about exactly what is science can sometimes cause more confusion than they do elucidation. I think that science, it should be about using objective reasoning as much as possible. Science is what we do to try and overcome our internal biases. when the wave theory of light was being proposed, this guy, I think it was Fresnel, I can't remember, but this guy said, okay, well, if there's a wave theory of light, then that means when it passes, if you put a disk in front of it, then you're going to get interference and ripples on the outside. And he proposed this to like maybe his thesis committee or something. And one of the professors said, well, but that's ridiculous, because if you do the math, then that means that if you have a big beam of light and then you put a solid object right here, light, solid object, then right in the middle of the shadow, according to your silly idea, there should be a bright spot. And that's absurd. And then the other people on the committee were like, well, that does sound absurd, but we should probably check. We should do the experiment. We should make a thing of light, and then we should put a disk, and then we should see maybe there is a bright spot in the middle of the shadow, even though that seems absurd. And they checked, and there was a bright spot. And boom, wave theory of light, way more convincing than it was before. And the guy who is a legit, highly trained for, the 17 or 1800s scientist or physicist or naturalist or whatever they called him, he was just like, that's absurd, but he was just wrong. And that is so science can't be pigeonholed. It's about using observations of reality to try and create the most parsimonious models of reality that still describe all the data. And the way that you create a scientific hypothesis is you attempt to create a model that allows you to predict future data. The prediction of future data is how you evaluate if a scientific hypothesis has been supported or not supported. Is how well data that at the time of conceiving of the hypothesis was not known by the person conceiving it. The data itself could be old, but if you haven't analyzed it, if you haven't checked, if you're like, oh man, it would be really awesome if somebody could do the mass spectrometry of ice and water and show that they're the same, and you make a prediction and you don't even know that somebody's already done it, but then somebody else is like, oh yeah, they have done that. You have predicted that data because you didn't know about it. For you, that data was still in your future. So yeah, science. But the book I wanted to recommend was The Beginning of Infinity, Explanations That Transform the World, I believe is what it's called, by David Deutsch, who is a British computational quantum physicist.
One more time for the book.
The Beginning of Infinity, Explanations That Transform the World.
Okay. David Deutsch.
David Deutsch.
Okay.
But science. The reason I like science is because it's awesome and it's interesting. And I think it's good. I think it helps humanity. I think that the most obviously successful investments that have been made into the future of humanity have been scientific endeavors. if you just pour money and resources and everything into understanding science, then I get rich. Sorry, I mean, then then everybody benefits. Not from every individual thing. The people in Hiroshima did not benefit from atomic theory. But has your average person living today benefited from it? I would say so. But it's very hard to pigeonhole. You shouldn't pigeonhole science. I remember I was talking with Nathan Thompson for a hot second. And I was explaining how we in our lab create a localized gas right next to a vacuum, and his response was, "That's not an experiment." And I was just like, "What? What?
Yeah.
That I don't. Yeah.
That one that kind of sounds like an experiment. I mean, you're
Yeah, right?
demonstrating an
Like,
apparatus.
what's an experiment? An
I,
experiment is when you try and test an idea in a systematic way.
Can I go go back to that thing with like with atomic theory with Hiroshima versus nowadays? I gotta interject, and I just want to
Yeah,
ask.
that's actually like if you were to disagree with me, that would be one of the things I could least well defend.
Yeah.
Would be nuclear theory. It's the example that is most obviously against the point I am making.
Do you think that it is possible that instead of having to have some people like in such a horrendous way experience us learning, like we can learn without needing to
Yeah, we didn't learn
quote,
anything
quote,
from
quote.
that. We learned
Yeah.
from the Trinity experiment. We didn't learn from Hiroshima.
Okay. Yeah. Okay.
Nobody died from Trinity.
Yeah. Or learned what not to do, or what is
Yes.
the most futile thing.
Yes.
Is okay. Well, that was wow. Michael, thank you. Really.
Thank you.
For
You've
this.
been a wonderful interlocutor. It's been really
Very kind, man. It's
I would love to have more discussions. We could even make this like a semi-regular thing if you want.
yeah. I dig it. Um. Okay. Definitely. Yeah, man. You're fun to talk with, and yeah. We'll talk. We'll be in contact because communication is an amazing thing. All right. Any last?
Stay curious. Curiosity. The reason I wanted to talk to you is you seem genuinely curious. And by the way, you also are the arguments that you have put forth for flat Earth. There's one in particular that I'm thinking of. This atmospheric argument where the guy opened the door to the room and the cold air came in and it made all of the like candles or whatever like suddenly start to loom a whole lot. You're trying to sort of demonstrate the same kind of thing that could happen with like
Temperature variation, like
yeah.
observed in the natural world. There's temperature variation.
You sort of came out and you were saying like it like look, they look like they're cut off from like the bottom up, and this is all on a flat thing. That is the best experimental argument I've ever seen in Flavor of the Flat Earth. I mean, it's bad. It's bad for a lot of reasons.
Well, it shows that it's like plausible that you can use a variable.
You were able to show a situation that actually, like, yes, it was showing what you were claiming it was showing, and that was it was very effective at that. And your example was correct. It's not applicable for other reasons, but I remember watching. I think it was in a debate that you were having with Leo and Mark, and their responses to it. Like if I had been debating you, I would have been like, that like, yeah, under those circumstances, you're right. It can look the same, and as I recall, they were kind of like, yeah, but it's not cutting it like halfway up, and it just clearly was. So
That's
I wanted to give you
mean,
that point, that like you actually made an argument. I was like, you know what? Out of, if I had to show people one experiment to support flat Earth, it would have been that particular example. Which again, I do not agree with, but
yeah.
yeah.
Absolutely. But that is, I mean, and I think that does show a lot of integrity, that you're willing to have the conversation and really look objectively at everything and say, okay, what is, does this support this, or can it
Yeah.
support it? And just to say, you know what, give points where they're due. I think that's I
For the
think
record,
that should be.
like, I expected there to be another factor of 10 here. I expected this to give like 30,000 meters instead of 3,000.
Yeah,
I
but
was
that
surprised how
even
small it was.
30,000, 3,000, that's within
Yeah,
a range that is
it's not crazy.
within the claim.
Yeah,
So
yeah,
that it's all, and that's like all of us like working together, even not just pick any topic, but trying to accumulate as many points, and then cipher through what works, and sift through it all, and then we will all, as a community, science as a community, like, you're left with the most plausible, and in whatever topic it may be, physics or biology or wherever, hopefully we can use it to help everybody out, have a fantastic quality of life, and be able to enjoy each other's company. So
yep,
okay, Michael, I'll well, I think we can wrap this one up here. It's been a pleasure.
absolutely. I hope
Yeah,
we can do
man.
it again soon.
Yes, for sure. All right, peace be with you all. Have a good one.
Bye, everyone.